In this video, I'll be looking at work done along an inclined plane. Now, an inclined plane is a plane that is tilted, a slopy plane that is kind of having some angle of inclination. Like this, my ruler, if I place it like this, of course, this is horizontal. If I raise this ruler up, such that there is an angle between this level of my ruler and this horizontal, it means that the surface of this ruler is inclined at a certain angle theta to the horizontal. And then just like you have here, this is a surface that is inclined. And on your inclined surface, you have this box of mass M. Now, of course, in other aspects of physics, this arrangement, this system is called a simple machine because by means of this, loads can be lifted from this level A along the plane to this level B. So we're not looking at that aspect now or resolving it as a machine. We're just trying to see the work that is done using this arrangement, this inclined plane, to move this block of mass M along this slope to this from point A to point B. Now you agree with me that this level A is the same thing as level C. So taking this block along this plane from A to B is the same. I want to prove to you that the work done taking this block of mass M along this plane to point B is the same as taking the block. If the block were here, I want to raise it vertically upward from point C to point B. The work done is the same. How do we show that the work done is the same? Because that's one thing about work done in the gravitational field, that the path taken is immaterial. If work is done in the gravitational field, doesn't matter the path followed, as long as you are getting to the same point. I'm getting to point B. Either I take through A to B or take from C to B. The work done is the same. Now let's do the analysis of this object on this line on this inclined plane. Now, first of all, I need to talk about the weight of this block. The weight of a body is always acting vertically downwards. So with the aid of my ruler, I'm going to draw a line showing the weight of this block acting this way, vertically downward. And W is the symbol, which is equal to mass times acceleration into gravity. That's the weight of the body. Now, since this body rests on this inclined surface, there is another force. We call that the normal force or the normal reaction. And the normal reaction always acts at right angles to the surface of the block. I mean, to the inclined surface, not surface of the block. Now, I'm going to take my ruler and produce a line like this. Now, this line is called the normal reaction, called that R. You can see that it acts at an angle, right angles rather, to the inclined surface. So that if possible, I can produce this line down with this broken line. The normal reaction can be extended so that the angle between the weight line and the normal reaction line produced is still theta, which is my angle of inclination. So this theta is my angle of inclination, and this theta is also the same angle of inclination. Now the length of the plane is given as L, measured in meters or in centimeters as the case may be, and h is the height of the plane. Now I will need to resolve the weight of this block. The weight of this block has two components. Using this right angle triangle, there's a component of the weight of the block which is acting along the hypotenuse of this right angle triangle that is acting along the plane. A component of the weight mg acts parallel to the plane, acts down the plane. So we call that can I call that the x component? The x component acts, we can call that the component of the weight acting along the plane or acting down the plane, or that acts parallel to the plane. So that is the x component of the weight mg. We need to find an expression for the x component of the weight mg by using the same nomenclature. And if I do that, I'm going to say this is opposite because the same x component acting this way is the same thing as the one acting in this on this side of the right angle triangle. So this is my x component. So can find out by using sine. So my sine theta is equal to opposite x over hypotenuse mg. So it means that my x component is mg sine theta. Okay, that's my mg sine theta. And you can also see the direction. The direction of mg sine theta is down the plane, parallel to the plane. Now my cosine component adjacent over hypotenuse that gives me mg cos theta. Now you can see here that there is no motion. The block does not move along this line. It means that the normal reaction is balanced, is cancelled out by force mg cos theta. So force mg cos theta balances the normal reaction. And that's why there's no motion in this direction. But now you agree with me that it's possible. There's a certain angle of this inclination such that when even if you don't touch, no action, no applied force is made on the block of mass, on its own it slides down. There's an angle of inclination that will make this start moving on its own, even without a touch. It means that the mg sin theta is that force responsible that pulls it in this direction, even without you touching it. On its own, just keep this thing like this. Just drop your pen. Just see the pen rolling down along my own inclined plane. It means that mg sin theta is the force that is actually responsible for the motion, downward motion of the this. And this mg sin theta, you can see clearly that it is mg is constant. Sin theta is directly proportional to theta. It means that the angle of its slope increases, sin theta increases, and so also mg sin theta equally increases. Okay, so that's why there's a certain angle of the slope that will make this one just begin to slide down, even without an application of an external force. All right, so and in this case, suppose the slope is smooth. Let's start with having an inclined surface that is smooth, perfectly smooth, so that the coefficient of friction mu is equal to 0. Remember that the coefficient of friction is defined as frictional force divided by the normal reaction. Okay, so this is how we define the coefficient of friction. So for a perfectly smooth surface, that coefficient of friction is 0. And that means a friction force is absent in this situation. Okay, it means that the minimum force, because work done taking this block from point A to point B still remains the product of force and distance moved in the direction of the force. And the distance d is the length of the plane. Okay, distance d is the length of the plane measured in meters. So I can use D, I can use L. All right, but this force F, for smooth surface, this force F becomes the minimum. So what's the minimum force required to do that? Force F will be equal to mg sin theta. Why is it so? Because since there's no friction, the only force acting along the plane is mg sin theta, and it acts in a direction to bring down this block of mass, back to point A. So if I must overcome this mg sin theta, I must apply a force F, which at least must balance this mg sin theta, must at least be equal to mg sin theta if this block must be moved along this plane with a constant speed. With a constant speed, it means that this F here must be equal to mg sin theta. So when that happens, it means that the work done in doing this will be minimum. So in exam conditions, they may give you a situation like this and say, calculate the minimum work done. What is the minimum work done in raising this block of mass from point A along this inclined plane to point B? So that minimum work done, let me call that Wm, is equal to mg sin theta multiplied by the distance L, which is in the same direction as the direction of the force F. Okay, so you can see here that mg sin theta, mg L sin theta is the formula for calculating the minimum force. In some instances or cases, they will not even give you all these parameters. You will not be given the length of the plane. But how can you find an expression for sine theta? If you come back to this picture, you agree with me that this is a right angle triangle, that is ABC is a right angle triangle. And by SOHCAHTOA, I can have my sine theta is equal to opposite h. That's the opposite side over hypotenuse, which is the length of the plane L. So if I come here and make a replacement, a substitution, I'm going to have the minimum work done Wm is equal to mgl. Sin theta has already been found as h over L. So this L will cancel out this L. So that the minimum work done in taking this block of mass from point A to point B along this frictionless, along this smooth inclined plane is just simply equal to mg times h. The product of the mass, acceleration due to gravity, and the height of the plane. So it does not matter. I was telling you the other time that it doesn't matter the path you follow. As long as you are bringing this block of mass to the same level B, whether it take through A or take through B, or maybe the block of mass was here, the same level, and you are coming to this one point B, the same work is done. That's why the gravitational field is a conservative field, that energy is not lost, work done is not lost. Doesn't matter the path you follow, the work done remains the same, irrespective of the path that is taken. So if I were to raise this block up, maybe this block was here at the same level, you can see that with level A, vertically upwards to point B, my work done is still mgh. So whether you follow along this line or you follow this vertical path, the work done is the same. All right, so in the next video, I'm going to solve one or two questions on this aspect of work done moving along an inclined plane.